I will use a resistor as a load. Last time. The question is, it's a 3 lambda by 4 section and the lambda by 4 section behave the same way.
We have the more phase will match with the two states. That's like this one is the electrical.
Yeah.
That is.
Right, but remember when we say we're looking at an impedance transformer, we're looking at one particular frequency. Right? So the exact behavior happens only at that frequency. What do you expect? Anybody? Priyanka? Who was so apart from Manojit, there was a second student from DMAP that was good. You didn't email me saying that I want to join this class. Did you?
That's one.
Oh, that is Manojit. So who's?
I'm sure.
You mean?
That meant
You mean when? Oh. Just before coming to class. Was there somebody else from DMAP? You're also going to take it for credit?
yes, but I'm not really.
Yeah, please email me so that I can send you emails about the class. All right, so here's we are now at the standard situation. So let's remind ourselves once again, blue is real part. So the transform value is 250 ohms, imaginary part goes to 0 at 6 gigahertz. I'm going to freeze this.
Hello, sir. I can't see the screen.
Sorry, 1 second. You didn't miss much. I was just drawing it. So here. Now should be able to see.
Yeah.
So maybe just for completion, what I have done is drawn a lambda by 4 section, 50 ohm, 6 gigahertz, 90 degrees, 10 ohm load resistor, and we're looking at Z in as a function of frequency. And as we saw exactly at quarter wave, at the frequency for which the section is quarter wave, the reactance is, the imaginary part is 0, and the real part is 250 ohms, which is what we saw yesterday, right? That's the transform value. This 250 basically comes from Z naught square over RL, right? So it's 50 ohms, so 50 square is 2500 divided by 10 is 250. That's why this is 2. The question now is, so in fact, let's maybe a little bit more precise. Let me add the marker here, and that's there. I'm going to adjust the characteristic impedance of the transformer so that I match it to 50 ohms. So I want this value to be 50 ohms. So I'm going to have to decrease this. That's close now. Here's a graph.
Will there be a difference in the fall?
Sorry,
Will there be a difference in the fall amount for the yes.
fall amount with the shape. Okay, anybody else? Aishi? Otherwise, am I saying your name correctly? Aishi, right? Okay.
The matching will be of
So let's do it as a suspense. I'm going to just give 1.6 gigahertz. So you can see that there are those points there now. It's only solving for 6 gigahertz. I'm going to change the transformer now to 3 lambda by 4. So that's going to be how many degrees? So I've run it. It's back there, right? Just to verify, let's tune it. See, it varies. And if I come to 270, it comes back exactly this point. Any other thoughts? Will the curve be the same if I plot all the frequencies? Will it be different? Like Vanya was suggesting that it might, like how quickly it falls off might change.
I think the imaginary part will be minus of the digit curve. I mean,
Well, here of course it will be 0. You're saying that instead of like this, it might go like that. Okay. Anything else? Gaurav? So, Tanya, will it be, do you think it will be falling off faster? I should probably do it here. So, do you think it will fall off faster or it will fall off slower?
So 270 fall
Faster. Still retaining some amount of suspense. Ooh. My curve was almost exactly right. I didn't practice it. So both of you were not right. It is faster, but the imaginary part is not changing the sign. Let me see what happens if I put 180 degrees. So that would not be a lambda by 4 transformer anymore. So it's not going to do this. So what did I say happens for lambda by 2? No. Not in this case. So for lambda by 2, like suspense. Go back to
It doesn't.
sorry, 180. So its value is 10 ohms at 6 gigahertz, and the imaginary part is 0 because The load is RL equal to 10, XL equal to 0. So lambda by 2 or lambda or n lambda by 2 retains the impedance. Whatever you had, it comes back at exactly that point. But now coming to Suraj, right? To your point, if I now sweep this frequency here, right? Now it gives you the opposite sign. So the two are not really connected in terms of their operation, but the sign change happens every lambda by 4, and that's why here at lambda by 2 you get the opposite behavior. And, it's put 0 because we put a real load there. So let's go back to 270. And now plot over the full range where we were looking earlier. One. Now we see some more. So initially we were only focused on the central part, which is we said that it's going to have a faster follow. So that immediately tells you, and by the way, the faster follow is happening in the imaginary part as well, right? So this is much steeper than this curve. So it's changing a lot more faster. So using a 3 lambda by 4 instead of lambda by 4, which is silly just in general because why use a longer length? It's also bad because it will actually give you a narrower bandwidth for match. Unless, of course, that's what you're aiming for. There could be a practical reason in an experiment where you want that impedance match to actually be narrower and only want to work. What does this mean? It sort of acts like a filter, right? It's not going to match it over a large range of frequencies, but you want the matching to happen at that particular frequency. So maybe your system has noise and you want that noise not to couple over a broad range of frequencies. So one could use a trick like this. There are, of course, many other ways of doing this, but I just wanted to point out that it's not equivalent in all senses. So this idea again, it's simple, but I want to emphasize it again and again that whenever we work with transmission line sections and we talk about impedance matching, the exact matching condition is always at one frequency. And how things change from there will depend on various other factors. Is it lambda by 4? Is it 3 lambda by 4? And this thing also happens for the case of the lambda by 2 thing which we just saw. So here you see this opposite sign. But if I now go to 1 lambda, which is 360 degrees, so you see the same thing happens, it just shrinks. Right? So it's sort of indirectly connected to what Panya was earlier saying, that you get these repeated things, and that basically means you're now squishing many more periods in the same frequency space. Now, what does that actually mean in terms of this multiple peaks? So let's go back to 270 degrees here. Let me clear these things. So we were, of course, initially interested in this frequency here at 6 gigahertz, but now this looks exactly the same, right? If I did not tell you the frequency x-axis, you cannot distinguish between this and this. So what do these points represent? Let's start with the low frequency point, which is happening at, any guesses what this frequency is? It's 2 gigahertz, right? So it's exactly matched again. It has 50 ohms at real part and imaginary part is 0. Why is this working?
Last time you said about the product of beta egg.
Yeah,
So has it got to do with that?
sort of, but how will I think of this? This looks like a lambda by 4 transformer, right? In terms of its frequency response, it's matching it to 50 ohms. Imaginary part is 0, so it's a proper match. How will I think about that response for this 270-degree?
It's something like that.
We're going all over the place now. It's not, it's very straightforward. I mean, something related to what she said earlier. But what is, it is obviously related to the beta because there's only one thing which is changing in this formula, right? We are fixed right now. Z0 is fixed, ZRL is fixed. Z0, your source impedance is also 50 ohms. So the only thing that can change is that tan term. Why is it also getting matched here? Look at the light curve in the background, which was for the actual lambda by 4, which was 90 degrees. You did not see any such match anywhere else, at least at lower frequencies. I mean, come on, this has to be obvious by now. Gaurav? I mean, it has to be lambda by 4, right? It's a lambda by, it looking exactly like a lambda by 4 transformer, so it has to be a lambda by 4 transformer. But Manojit, any ideas?
If we take a 3 lambda by 4, obviously the reduce the lambda by 4 happens.
Yeah. So this was your lambda by 4. Video is not there. So this was lambda by 4 we started with, but at 6 gigahertz. Now I'm looking at a response which is 3 lambda by 4, 3 times longer at 6 gigahertz. But at 2 gigahertz, which is 3 times lower in frequency, hence all the wavelengths are 3 times longer. This is lambda by 4. It's lambda by 4 at 2 gigahertz. That's why it's matching at 2 gigahertz. That's it. So if you choose some arbitrary length, you're going to get matches at various frequencies, starting with the lowest frequency where you can get a lambda by 4. If your length is not long enough, you will not reach lambda by 4 at those lower frequencies. So when we started with 90 degrees, that was the shortest length. It was the length for lambda by 4 at 6 gigahertz. So for lower frequencies, it will always be less than lambda by 4. But when we went to 3 lambda by 4, at f over 3, it's lambda by 4.
So it is depending on the beta. I mean, beta is 2% of omega root over of Celsius. So I think that is related to that.
Yeah, exactly. So now what has happened is L has become 3 times. So in order for beta to become 3 times smaller, I have to bring the frequency 3 times smaller. So instead of 6 gigahertz, now it's a lambda by 4 at 2 gigahertz. And then what about this peak out here?
So it is another full wavelength.
So this is at this frequency. So again, remember that when I talk about impedance matching, you have always talk in respect to the frequency at which we are looking at. Initially, we were looking at 6 gigahertz. Earlier, 90 degree, the transmission line I made was lambda by 4 at 6 gigahertz. Now I have made something which is 3 lambda by 4 at 6 gigahertz. That's why it's lambda by 4 at 2 gigahertz. Now I'm at some other frequency. What does this frequency look like? It's 10 gigahertz, right? It's 5 lambda by 4 at 10 gigahertz. So it's the next iteration of this periodic behavior.
So, sir, one question.
Yeah.
So for earlier case, when you fix the lambda by 4 for 6 gigahertz, so you should get 3 lambda for 18 gigahertz.
Absolutely. You can check that. Let's go to 20. Wait. Here. This thing will just stretch and skew depending on what the numbers are. Now it's exactly as we said at 18 gigahertz here. It's back to. Okay, so is this part clear? A transformer at one frequency could be a different transformer at a different frequency. So one has to keep that in mind. A very subtle question. When asking the question is what? Let's see. Clear the part. So now we're looking at full 1 to 20 gigahertz. It's 3 lambda by 4 at 6 is the definition. So it's lambda by 4 at 2. 3 lambda by 4, 5 lambda by 4. Just a little while back, we discussed the difference between using a lambda by 4 and a 3 lambda by 4 in terms of its frequency response. We saw that it drops off faster. These curves are showing different effective transformer lengths, some periods of lambda by 4, multiples of lambda by 4, at different frequencies. If you look at the curves, they all look the same. Do you notice that? The width of these curves or the slope of the imaginary part around 0, it looks exactly the same. Like visually. How do I reconcile these 2 points? Or is there nothing to be reconciled? It's a trick question.
How do you differentiate between two similar? They have all of them.
Yes, but what I'm saying is that we saw that a 3 lambda by 4 transformer falls off faster compared to a lambda by 4 transformer. So if I had actually gone to a 5 lambda by 4 transformer, it would have been even sharper. Now, this first point here, the lowest frequency, is a lambda by 4 transformer. This is a 3 lambda by 4 transformer. This is a 5 lambda by 4 transformer. But they all look identical. You understand what I mean by identical, right? So if I look at this spacing in frequency space, they all look exactly the same. It seems to, I'm saying it's a trick question. It seems to counter the argument which we just made and actually saw.
Yes,
Sorry, maybe somebody else can. Will you raise your hand? Yeah.
So, initially, what you have shown that was related to the length of the transmission.
The transmission line.
Right. So you reduce the length, or reduce or increase the length, but that is only the frequency.
That is correct, but it is still, the lowest one is still a lambda by 4 transformer at 2 gigahertz. This is a 3 lambda by 4 transformer at 6 gigahertz. As I said, my formulation of the question has a lie or a false aspect to it. I'm just asking you to catch that. Yeah.
So earlier we had seen that the fall off was happening when we were considering lambda by 4 versus 3 lambda by 4 at 60 gigahertz. And now we are just replace the parameter.
Because every time the transformer is going from lambda by 4 to 3 lambda by 4, the frequency is also going from F to 3F, and so on and so on, 5F, 7F, and so on. So the reason I was trying to emphasize this point is that we talked about this idea of fractional bandwidths, right? The absolute bandwidth, if I define those, those arrows as whatever I've drawn there, because they look the same, but the fractional bandwidth is actually getting smaller, because what is a fractional bandwidth? It's with respect to the frequency. So if this number is here is say 200 megahertz, 200 megahertz at 2 gigahertz is a wide band transformer, as opposed to 200 megahertz at 18 gigahertz, because 200 over 18, it's a much smaller fraction of the operating frequency. Right? So this again is something which happens a lot in these kind of structures. The higher the frequency you go, for the same fractional bandwidth, you will get more absolute bandwidth. Here it's the opposite effect. It's the same absolute bandwidth, but you're going to higher frequencies, so the fractional bandwidth is getting smaller. So the correct statement about what a lambda by 4 versus a 5 lambda by 4 or 3 lambda by 4 transformer is in terms of bandwidth is that it changes the fractional bandwidth. It will reduce it. But for a single section of line, that response is exactly the same as you go from one to other. Okay. Any other doubts or questions at this point? Let's go back here. So Posa also discusses the case of open circuit as well. And now the curves just look shifted. Suppose infinite at 0 and then goes to 0 at lambda by 4. So again, it's inverting the impedance. It was infinite. It has become 0 at lambda by 4. And in connection with this idea of, I mentioned that it's difficult to make ideal shorts and opens. You could probably guess that it's an open is sort of more ideal than a short circuit, because having a wire with 0 inductance is harder. So sometimes we actually create a short circuit. If you want a short circuit at a particular frequency, this is one way to create it. You take a lambda by 4 section of transmission line, which is open at one end, but at the other end, at that particular frequency, it will look like a short circuit. So these kind of again sections are useful in building filters and other kinds of responses. Just maybe one other point. If you look at this voltage and current, plus of course the ratio of those two is what is giving you the impedance, because it's just the ratio. So whenever current goes to 0, impedance goes to infinite, and whenever voltage goes to 0, the impedance goes to 0. And the same way over here. But this is I just want to point one interesting part here is that if I have a transmission line which is lambda by 4, and I send in some wave here, it reflects back at an open end. So here the CL is infinite. Then if I want to see, so remember that there is some other transmission line here, and this is the boundary here. the waves are coming from here. And it goes, reflects, and comes back. And we are looking at this point, which is lambda by 4 from this end, which is basically these points. So here it says that the voltage actually goes to 0. Which means that if I have some device which is connected to this point, so if I connect some device here, let's say for inside of B, then this device will not experience any voltage drop across it. Even though it is connected to that line, because of the interference between the waves going this direction and the waves going this direction, at exactly that point, it will not see any voltage drop. So it sort of is completely isolated from the system, even though it is connected there. This is just a small side point. We will come to these kind of things later on. The reason I mentioned this is that these kind of ideas of looking at places where voltage is 0, equivalently there are places where currents are 0. Right? So there, of course, what you have, the thing which will get unaffected is something which is in series with the transmission line. So if I go here, so I see current is 0 at this point. So if I have O lambda by 2 and I connect something between two transmission lines, so the device is sort of here. This is now lambda by 2. This is CL equals finite. Now I connect my device here. Then even though waves are coming here and waves are going that way, at that particular point there will be no current in that device. So these kind of ideas can be useful where you're trying to protect a device from an external stimuli, or you want to combine low frequency and high frequency things together. Because remember that this only happens at a particular frequency. So this protection or isolation happens at one particular frequency, but at other frequencies you can get things in. So something similar to it, we will look at an example much later in the course, that in microwave circuits, sometimes when you're trying to combine DC and AC signals, and this is something people in Mandar's group often try to do these days, you have to be very careful, because again, just putting something to apply a DC voltage could be very, it could be disastrous for the RF problems. So one good place to put them are in such locations, because it will, that at RF, at microwave frequencies, you will just not even see that connection. But at low frequency, at DC, it could perfectly pass a current through it. Okay, so right now I'm being a bit vague. I will give specific examples of these kind of circuits. So of course, this is see that the open circuit you get caught beta L, and then this idea that length is lambda by 2, ZL is exactly equal to ZL. So it's something we already saw, and for lambda by 4 you get this formula. So we will now look at this. So this is so this is again has some subtle concepts here, so I want you to pay attention carefully. The picture is of two transmission lines. Both are semi-infinite in one direction. Okay, so Z0 is going this way, it's infinite. Z1 is going this way. And what we are interested in is what happens to a wave which is propagating from left to right at this junction. And the difference between these two transmission lines is that their characteristic impedances are. Now, obviously, since the characteristic impedances are different, you're going to get reflections at that point. The question is, how do you compute that reflection? Right? there are few ways of looking at it. The subtle aspect is related to this idea that this is an infinite line. Why do we need an infinite line? It's to prevent multiple reflections, so that we are only able to think about this boundary and not anything else. So when a wave comes from left, comes to this boundary, there will be one reflected wave and one transmitted wave, but the transmitted wave never comes back. We will see just in a little bit that what happens when you have such waves which are transmitted at one junction coming back into the system as well. But even, and there the idea is that at a time local, so as a point local in time, if we are now really, remember that we are now thinking in the time domain, not in the frequency domain, right? This is a pulse or some wave which is entering this junction, this interface, and then we are seeing what happens after that. One way, practical way of ensuring, of course, that this wave here never comes back is to put a termination here. So some load, which is R, which is equal to C1. Because that would be a matched load. And then this transmitted wave will get absorbed here. So here's a slight digression and a deep point, which we will come to much later. It's actually more to do with physics than engineering. I said two things in the last 5 minutes. I have an infinite line, a wave which once goes on that never comes back. I just said that practically, you can't have an infinite line in real life. Practically speaking, I could just terminate it with a matched load so that that power is absorbed and then nothing comes back. If I try to equate these two ideas, it tells me that an infinite transmission line is equal to a matched load. It's equal to a matched load. It's equal to a resistor. So in this case, of course, we have to deal only with real characteristic impedances and real loads. And there will be a problem about this later on. But this is actually there's a deep connection to physics fluctuation dissipation theorem about this. So let me just spend one more minute to make you very confused. This transmission line is made out of the simple model out of inductors and capacitors, which have no resistance in them. In the ideal case, right? They are just reactances. I now have an infinite array of them. And if I look at the input impedance of this transmission line, it looks like a resistor. Think about it for 30 seconds and then we will move on. I have created a dissipative element out of purely reactive elements. Right? I could make a circuit with LC, 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 LC. I need an infinite number of them. But from one terminal, it looks like a resistor. The significance of this from the physics side is it turns out that there is no simple way to write down a Hamiltonian, a quantum mechanical Hamiltonian for a dissipative element. It just doesn't fall in the framework. But by using an infinite number of reactive components, so it's later on, I mean, I might give some example, even though it's not really part of the scope of this course. You can write down now a quantum mechanical Hamiltonian because it's now an infinite array of things for which you can write down Hamiltonian. Of course, because things are infinite, you have to take some limits and other things. But this was a big development in this, something called Caldera-Leggett decomposition. Because you couldn't write dissipation into in a quantum mechanical way. But one can actually derive this fact that summing an infinite array of L's and C's can actually give you an impedance which is real. Practically speaking, from the point of view of what happens in the wave picture, it makes sense, right? We're just talking about some kind of an equivalent model, so maybe there's nothing to be very worried about. A matched load ensures there is no reflection. An infinite transmission line ensures there is no reflection. So you cannot distinguish between these two cases. One other point before you continue this discussion is, in reality, in practice, the infinite nature of that transmission line is not important, as long, or I can say that it's equivalent to a situation where the time over which you are interested in, like the time in your experiment or in your analysis over which you're interested, is long enough that the wave which travels here and then comes back, it is much shorter than that time, or it's actually just shorter than that time, then that is equivalent to it being infinite. So that's why in this picture, locally in time, we can make this assumption that, okay, I only have to worry about a transmission line coming in of Z0 and a transmission line going out of Z1. As long as there is no time for the reflected wave to come back, if I finish my analysis or whatever I'm doing in a time much shorter, it's exactly the same situation. So then it's very straightforward, because then you can now think about this in various ways. One is that you have a matched load of Z1, and remember, matched load of Z1 connected to a transmission line of Z1 is its input impedance is going to be just Z1, right? It doesn't, remember we had discussed this, that if you have a matched load and you can put any length of transmission line, it just looks like the same impedance there. So then all we have to do is, you at this junction you put a load which is Z1, and then you can compute the reflection coefficient, right, which is just Z1 minus 0 over Z1 plus 0. But because you know that it's actually not a load but a transmission line of characteristic impedance Z1, you can also compute the transmission coefficient, which is this here, which is basically telling you, okay, whatever has not reflected must be transmitted. And again, by writing down wave equations on lines at z less than 0, so this point is being defined as z equal to 0. So again, if you remember from your quantum mechanics problems of the potential well, you have your wave function on one side, you have your wave function on the other side, you do the matching of the boundary conditions, it's exactly the same, right? That's what you're doing here. You write down the wave equation on the left side, you write down the wave equation on the right side, and then on the right side, you're only writing right propagating waves. Whereas on the left side, you're writing both right and left propagating waves. You do the matching, and then that gives you this coefficient P, which is basically the amplitude of the right propagating wave on the C1 transmission line. And you get this. So this way, at a boundary, you can compute how much wave will go to the next transmission line. So here, the transmission coefficient is sort of equivalent to the power delivered to a load which we had calculated when we terminated a transmission line. And sometimes this quantity here is also defined as an insertion loss. So it's because that the presence of that transmission line there has resulted in a loss of this amount of power which is related to the transmission coefficient. So again, this is just a terminology. Insertion loss comes in several places. Okay, so now last bit. We'll come back to the Smith chart in later class. I think I mentioned this, that it's basically a polar plot looking at real and imaginary parts. It's not really useful these days because everything is on the computer. This basically allows you to have some standard rules for looking at responses on a strip chart, and then you can easily learn about those responses. But we look at that. So the last part is basically to look at the quarter wave transformer in a slightly different way, which is related to this idea of reflections at boundaries. So this impedance point of view is something which we have already looked at. And I think Surat, we anyway figured it out, but you have to divide by tan on numerator and denominator before you take the limits. Otherwise, you just don't get the right answer. So when you do this lambda by 4, you get C in is just 1 square over L. Or if you want to find out what is the impedance you need to match Z0 to RL, that is, it is the geometric mean of these. So here, one thing to remember is that because you have matched Z0 to Z in, which is the input impedance at this point, and that's the combined impedance of the load and the transmission line Z1, this thing here. There is no reflection gamma, so gamma is 0. That's what the matching condition is here. So there are no reflected waves going in this direction, so this doesn't exist. However, in between these 2 points, there are waves both going in this direction and in this direction. So there will be standing waves in that quarter wave transformer section, and it's the interference between those waves which can also be thought of as giving rise to this behavior. So this is again just instructive to think about it, but not really, so useful. So in some cases, it comes in handy to get an intuition for what is happening. So this is to look at the multiple reflection point of view based on that analysis we just did about how to think about waves at a boundary between 2 different transmission lines of different characteristic impedance. How do you actually compute the net reflection coefficient? So there are now many things here. So let's go through it one by one. So here is the picture again. So at the bottom, you have a transmission line which is feeding this Z0. So that's our source. Then you have the quarter wave transformer of length L and characteristic impedance C1 and the load RL. So if you now look at this list here, let's go through it one by one. Gamma is the total reflection coefficient at this point, right? This gamma. That's what we are trying to calculate. Gamma 1 is the partial coefficient, reflection coefficient of wave incident from load Z1. So this, I think these descriptions are slightly miswritten here. He's calling it a load Z1, but it's actually a transmission line Z1, which is okay to be called a zone. So this gamma 1 is the reflection coefficient happening at this point, like shown here. And this is equal to just this value here, Z1 minus Z0 over Z1 plus Z0, because it's the impedance mismatch between those 2 transmission lines. Then you have gamma 2, which is the reflection coefficient coming in the other direction. Okay. So if wave was propagating from right to left, then you have the opposite situation that you have starting at Z1 and you're going into Z2. But that will just be the negative of that one. So it was only Z1 and Z0 and Z1 interchange position. So gamma 2 is minus gamma 1. So finally, you have gamma 3, which is the impedance, telling you the impedance mismatch between Z1 and RL. So that's just, and since RL is the load, and what's that? Stop. Was this periodic thing? We'll have a pulse tube on today. So note that these are the only things we need to know, right? You have this boundary and you have this boundary. There are only 2 boundaries here. So we have defined the reflection coefficients, but we also need the transmission coefficients here, which is basically how we had done earlier. Because at this point, at this boundary, there's going to be both reflected and transmitted waves, and similarly in the opposite direction. When you come from this side, there's going to be reflected waves and transmitted waves in this direction. So that's P1 and P2. Okay, and the expressions are given here, and T1 and T2, as we calculated earlier, can also be calculated the same way. Then this picture comes in of how you think about this whole thing in terms of multiple reflection. Right? So you first come in with a wave, it partially reflects, partially transmits. The partially transmitted wave undergoes a reflection with coefficient gamma 3, comes back here, and then gets partially transmitted with the coefficient transmission coefficient T2, but also reflects with a reflection coefficient gamma 2, and so on and so forth. So if you look at the total reflection at this boundary, at every such reflection. So again, remember, this is sort of an idealized picture. We are imagining that whatever this pulse we are sending in is much shorter in time than it takes for it to travel back and forth. Okay, but when you add this picture, then it no longer matters once you finish the calculation. This is just for the intuition for thinking about it. So the first reflection point has only a reflection coefficient gamma 1. So you assume that you're sending in a wave of amplitude 1. So the reflected wave is going to have an amplitude of gamma 1. The second set is the one which was transmitted the first time. So it went to, so that it picked up a transmission coefficient T1, gamma 3, and T2. So that's why you have this here. But there is an extra sign of minus because the total round trip from one end back to the other end back is lambda by 4 plus lambda by 4, which is lambda by 2, which is 180 degrees phase. So you get a negative sign. So then the next one, you can see that every time you go through it, you add an extra factor of gamma 2 and this gamma 3. So each successive reflection is going to give you a series like this, and you can imagine that for every successive reflection, is the magnitude going to change? Like, will this number be smaller than this one? Will this number be smaller than that one?
Between 0 and 1.
Yeah, but as we go to further and further, this amplitude is going to go down, right? Because each time you're working with a smaller amplitude than you started with the first time. So it's a series whose value is slowly going towards 0. So it can have a limiting sum. So that's what they do here. So the total gamma, which is what we're interested in, is the sum of this infinite series. You can go through the math here. It's a simple one. You can solve it for this infinite series. Then you get this complicated expression. But then you can use all the definitions you just wrote down in 2.64. So it's all the values of gamma 1, gamma 2, gamma 3, T1, and T2. You plug that in, and you get this form, which is basically what you would get if you had calculated gamma from the case of the math situation, and you want to equate this to 0, so that's the matching condition, and that gives you this same formula. So this is just to set up the equivalence that a time domain picture involving multiple reflections, or a frequency domain picture, which is the impedance description, will give you ultimately the same answer. But this will all work out only in steady state, like we talked about in the first lecture. But, there is other things going on. So if what basically it means is that if I actually send a pulse here on this line, so something finite, then the reflection coefficient, let me rephrase it. This is an impedance match situation, right? We have constructed an impedance matching lambda by 4 transformer. So we expect no power to get reflected. But if I look at it in time domain, the situation is slightly tricky, and this multiple reflection point of view allows you to think about it in one way. Is that the first time the wave hits that point, you're not going to get 0 reflection. It's going to take some time for it to reach this steady state, so that these multiple reflections have set up, and then you will reach a situation where it will be zero. Because we saw that it takes all of these multiple, and each successive reflection is going to take some time. In some sense, it will take infinite time to become truly zero. But since we are not usually worried about something being exactly zero here anyway, but this is not incompatible with the frequency domain picture as well. Because a pulse, any signal which starts at some point of time, is not a fixed frequency signal. So remember, impedance matching happens exactly at one frequency. So a 6 gigahertz frequency, let's say it was made for 6 gigahertz. When I send in at time t equal to 0, I turn the signal on. That is no longer a fixed frequency signal, right? Because it has this finite rise time. So that's another way of thinking about it, is that when you first start the 6 gigahertz wave, it actually has a finite bandwidth of signals around 6 gigahertz. Right? That depends on how sharply it rises, and it has some kind of a envelope. Right? This part, I hope you guys know. It's a Fourier transform ideas. Why this keeps, looks like if I don't do anything for a while, it stops the broadcast. So you can think of a starting of a pulse which starts at a particular time, even if those, let's say the frequency was exactly 6 gigahertz, means that initially you're going to get some reflections. But as the signal keeps, if it stays on, and it stays on for a long time, then you can, basically it starts approaching the situation where it's a pure tone. So something which is very long in time at a fixed frequency is going to have a very narrow frequency spread in the Fourier domain. So an infinitely long train, of course, will be a delta function in the frequency space, and that is the idealized situation of the frequency being exactly one value. So that's how you reconcile these two pictures. In practice, all of this will happen in no time, because you cannot distinguish between 0.01 versus 0.000001 in terms of gamma. If you're like trying to really look at how gamma changes as a function of time, just basically just have to look at the return power, right? You can measure it. You go very quickly, go to a small enough value that you won't be able to distinguish. But that's how you connect these 2 points, that the impedance matching is only at one frequency. Hence, you can never get a situation where when a wave starts, you're going to get no reflection. Just like when we talked about the an LC resonator, where in steady state it reflects the full power back, but it needs to first build up some power to reach that steady state. So that is a transient aspect. So similarly, this will also have a transient, but it quickly die down. So we can stop there, and let's see what else.
So I have a question.
Yes.
So, we have modeled the transmission line as parallel line. So we always mention what is the current in the above line. So what is the current in the below line?
So if it is a symmetric situation, then if it is really like two lines which are, then the currents in the two directions have to be the same. It will be equal and opposite. So this was something we had discussed, I think, in the first or second lecture. I don't know if you've had a chance to see the older ones. In most cases, the second conductor is a ground conductor. And we usually sort of not worry about the currents flowing in the ground conductor so much. But there has to be a path for the current to complete. So usually when we have two lines, we talk about voltage differences and the currents flowing in either direction. And this two line is just a model. I mean, you have seen that sometimes I will draw the transmission line as a coaxial thing. That's just out of habit. But the two line transmission line is just a model. In reality, the transmission line which we use practically have different shapes. Very rarely do we use these kind of two-line systems. There are some situations where we use them. But coaxial is the most common for sending signals outside of circuit boards. And then on circuit boards, there are different kinds of transmission lines. And that will be the next topic we will discuss after we discuss a little bit of Maxwell's equations and the connection of how to think about these things. Any other questions?
So you said that
Yeah.
when you have two transmission lines, this is Z0 and Z1.
Yeah.
So it's equivalent to having a Z1 load right at the junction.
If that Z1 line is infinitely long.
Then it's the same thing as having that.
Yes. Anybody else? All right, let's stop there.